Providing regulation of an escalating surge is the most difficult thing to do when you have a very good circuit idea, so good that it explodes with infinite gain, and quite rapidly as well. When you have that, you have a potential, like it's a sculpture in the rough, and it still has to be refined. So I borrowed an idea from my house of mirrors circuits, in which I use a battery with a reverse diode and a very high resistor in parallel with the capacitor of an arbitrary value in this case to regulate the surges that develop in this circuit. Now, this circuit doesn't work very well in the real simulator. It doesn't develop surges, but the LMD module does, and it does it so well that it's difficult to regulate, to try to figure out how to regulate the thing, because the thing wants to go to non-infinite matrix immediately. So different circuits respond under different circumstances, favorably or not so favorably. In this case, the realistic simulator, all the caps and coils have equivalent series resistance, which is a bit more realistic. That's why I call it that. It's a modification of Paul Falstad's electronic simulator in that he left out equivalent series resistance, but LT-Spice includes it by default, and you can change it. So I arbitrarily chose 10 milliohms per capacitor and 4 ohms per Henry per coil or per transformer coil, either kind of coil, or center tap transformer for that matter. And that does a very interesting thing. This particular configuration of caps and coils actually accelerates with the help of equivalent series resistance. Now, maybe I didn't put enough resistance in the coils. Of course, it's not a set amount like I did, a set ratio. I mean to say, it's a variable ratio. But the capacitors, it is a set amount based on the material of the dielectric. And I chose ceramic as my basis for what to conjecture would be a most popular use of a capacitor. Now, Wikipedia gives us these values for the capacitor, not for the coil. The coil, I picked an arbitrary value of 4 ohms per Henry. It could be very much higher, I don't know. So, what I did was, in fashioning this latest development, I had a really tough time working with the realistic simulator. These others, like this one for instance, are designed for the NE is the previous simulator, the one without equivalent series resistance, and Circuit Mod, which is the Java version. NE is the JavaScript. So they operate fine, but in the realistic simulator, they don't operate very well at all. They just take off, and the problem is they keep taking off. Even when you're in drainage mode, when you're supposedly diminishing, there it goes. See, it keeps going. So that's why I say this is specifically not for the realistic simulator. For the realistic simulator, I had a hard time with coming up with something that would not be like that one. Escalate under all conditions without any chance for regulation whatsoever. Until I came upon the idea, hey, why don't I borrow the idea from the House of Mirrors, in which I use a battery to regulate a surge, and I use a clock timer to turn off connection of the battery in parallel with the capacitor on and off, based on a duty cycle, in this case 85% duty cycle. So what does that mean? That means the battery is used 85% of the time to inhibit the escalation of a surge occurring due to these capacitors. And I also had to get the clock timer up to 100 kilohertz to do an adequate regulation. And I had to reduce the time step to 1 microsecond. my prior version, I manipulated time in order to try to regulate the surge. And then it dawned on me, wait a minute, this is something very fundamental. Regulate time? Isn't that what I do with the battery? So you see, there's always workaround solutions. Eric Dollard points this out, and how the power company makes it appear that the AC power coming from the power plant does not travel in time, or, excuse me, does not travel, well, it does not consume any time as it travels across space, and they do it by capacitors. Every 100 miles, a bank of capacitors as big as like several rooms, and they put the phase angle back in step with the power station, so you can keep extending that transmission line as many hundreds of miles as you like. And despite the speed of light limit to the speed of the electrical power going through the transmission line, the phase angle is made to appear as if no time has passed. In other words, the phase angle of the AC current will be in lockstep at the destination with by comparison to the source, the power station, as if no distance had been traveled. Well, that's faking overcoming the speed of light. So here we want to fake the manipulation of time, and we do it using a battery in parallel with the capacitors, since the capacitors are the ones running the show when it comes to surges. Because a battery is a fixed voltage, in this case 6 volts, and we put a reverse diode to prevent the battery from discharging, and a very large 100 mega ohm resistor to help reduce the amount of current overall, regardless of what direction the diode points it in, so that very little, if any, current will flow through that battery, in this case in a charging direction. All 4 of them are like that. And I reduced these capacitors to 27 millifarads to also reduce the rate of surge as much as I could. And I reduced the coils on the transformer to 1 Henry to match the 1 Henry coils of the motor coils, the 4 motor coils on two on either side. I think it works best to match them, and anything less than 1 Henry didn't seem to work, maybe for that reason, I'm not sure. So I have a clock controlling the opening and closing of these switches to connect these batteries in parallel with their associated capacitor. And then I have another switch here to disconnect the clock, to freeze these in a closed condition so that the battery locks in the voltage, the voltage level of the capacitor when we go into drainage mode. But when we go into surge mode, the clock is engaged, and thus the capacitors are allowed to surge at a regulated rate. Now there's one other thing I did that was quite novel. I learned that this regulates voltage of these motor coils, and if this is a high farad value, it will freeze the voltage value, whatever voltage value that these coils possess. And if you drop this down, it'll allow voltage to climb at the expense slightly of the amps. Now, if this were to be started up from a cold start with absolutely no charge, no pre-charge to any of the components, it'll take approximately, in this configuration, it takes approximately 2/3 of a second in real time to raise the current up to a level in which, when I disengage the surge and engage the drain, the current on the battery on the motor coils is what I want, the target of 50 amps for cruising speed, assuming I'm already got up to cruising speed. I already, used the throttle up to more than 50 amps, let's say 100 or 200 at the most, because 200 is generally the full throttle for a DC-oriented electric car. And I say DC, even though these are AC motors, because these motors have to be, actually should not be AC, they should be universal motors because they have to flip back and forth between the two states. When they're surging, they're AC. When they're draining, they're DC in terms of amperage. In terms of voltage, now they are DC as well, because I haven't gotten to why. Basically, I precharged C1. See, I've suspected for some time that Tesla did a little hooey, did a little subterfuge. He bought those radio tubes and wire, but he didn't use them. He took them to his hotel room. It was all a scam. It was a charade. What he really needed, and was inside that large box, was a single capacitor of very large farads to maintain the voltage he needed on the motors to provide the torque he needed to move around a 4,000-pound Pierce Arrow from 1931. You need a lot of torque, and you only get torque from voltage. You get speed from amperage. So this circuit is superb at developing amperage, but at the expense of voltage. It ends up with a piddly amount of volts, and it's not enough to run an EV. So it's taken me this long, a couple days, to figure out how to get around that problem. First of all, I learned to put a resistor in here to drop the voltage down to a ridiculous level in comparison to the amperage. Second of all, I replaced the resistor, and this is in parallel with the motor coils. I replaced this resistor with the capacitor, and thus I learned how to regulate the voltage on the motor coils. But now I pre-charge this capacitor, and it's a very high value, with 300 volts, assuming that's what my motor needs, 300 volts in order to operate. And it'll pretty much provide 300 volts to the motor coils without fail for quite a length of time without any diminishment, because the farads are so high, 470 kilofarads. Now obviously that's not realistic in terms of buildability, but in terms of the simulation, I could have gone higher. I could have gone up to 1 megafarad, but I chose 470 because that's the minimum I had to drop it to. In other words, I could drop it further, but the minimum I had to drop it from the 1 megafarad in order to get this thing to escalate from a cold start. So I keep that pre-programmed in here, and I keep the drain switch on because you got to transfer that voltage over to all of these coils on the transformer and the motor coils and the capacitors, because it'll shorten the length of time it takes to surge your amperage to your target. Because again, the amperage is starting from 0, even though the volts now is starting right off at 300 volts. So this is a very interesting situation in which we no longer use a battery as a voltage source and as a current drain. Instead, we use it strictly as a voltage source and not a battery, but as a capacitor, but of a very high value. And that's the way people are thinking these days, are trying to use capacitors in place of batteries, but they don't know to supplement that voltage with a current source coming from a pair of LMD analog computer modules put in series with each other. That's the part they're missing, plus the regulation of the surge to prevent it from exploding in your face. That's what the batteries are for. And that's why they don't have to be very large batteries. They just have to be batteries in good condition. And we preserve them to prevent them from becoming drained or something like that, or overcharged. But we do need them in good condition. There are no dead batteries in this circuit. So you have to toggle this switch, this drain surge switch, back and forth to help transfer power. And as you'll see, when I'll talk as I go. So we start up. Everything's from a cold start except this capacitor, which has 300 volts. And as you can see, it's supplying 300 volts to all 4 motor coils. But the amperage is still climbing. It's climbing because it's being transferred from this source. This is our voltage source now. So we go back to escalating surge mode, and it takes a little time. Let's reset this so we don't have to wait. So now we see that the amps are rising and the volts are dropping. And the amps are rising very slowly. So that's pretty good. So we could just leave it this way because it will take some time, or we can flip back and forth in hopes that it'll take less time, and it does not. So it looks like I gotta now stay in surge mode. Let's reset this. So we're slowly climbing to my target is usually 10 milliamps, because if it's 10 milliamps in surge mode, then I know when I flip the switch over to drainage, it'll be around 50 amps in drainage mode. And of course these volts will drop back down to the preset value of 300 volts. Right now it's undulating up and down. See, there it hit the nexus of the down point, and now it's rising back again. So it's going to undulate up and down is what it's going to do. And I only show one inductor for the voltage because that's all I have to show, because they both mirror images of each other. But amperage tends to go in inverted pairs. One goes positive and the other goes negative, and there's not much I can do about that. So my suggestion is, this is the way the coils are wound with respect to the direction of the coil, but when you place it on the motor coil, you place it any which way you want to get the thing to work. This is simply a wiring diagram. This is not a wiring diagram for the circuit, but not a wiring diagram for the motor. That's strictly something else entirely. I've never dealt with motors, and I don't plan to. I only deal with circuits. So this disparity between these two coils, or all four actually, they alternate. Two go positive and two go negative as far as amperage is concerned. Whoopsie, I'm talking so much I forgot to flip back over. So now I have too much amperage. I have 118 kiloamps, and as you can see, I have 300 volts. Exactly 300 volts, regardless of how many amps I deliver. Isn't that the most amazing circuit you ever did see? A circuit of constant voltage that never drains its voltage source, more or less, over time, because this is such a high farad capacitor, which is not realistic. Okay, so if it were more realistic, it would be drained. Let's just lower this and you'll see what I mean. So if I drop this down to 10 farads, now see, it's dropping. Let's drop it some more. See? It's dropping, and now it's going in the negative. We lost our positive charge. Can we get it back? Probably not. No, all we can do is stop the drainage, and now it's stuck in the negative zone to match the amperage. See? That's what I was getting, was each of these coils, these motor coils, were exhibiting positive versus negative voltage, and it was kind of crazy to match the positive negative amperage. But with the help of this, precharged, if you never drop it, it'll pretty much stay at 300 volts. So let's go back and get another instance of this. Start all over again. So it's not a perfect system. I'm still positive negative amps is a little weird, but the only thing you have to worry about is to when it comes time to wire, which direction do you wire the coils on the motor, that'll determine if you could arrange it so that they're all positives, to match a positive voltage, so that everything is matched in polarity. It's the way I imagine it. So you see the amps are rising, and of course I don't know what they're rising to, what value, and I don't want to find out. So I just, I start with drain in order to transfer, and then I go to surge in order to balance it out. Now you see everything's nicely charged. So maybe we'll go back here and see what happens. Now it's dropping. The amps are dropping, and so that's the right orientations that amps drop during drainage. For them to rise during drainage means that they're simply being transferred from this capacitor. Now that we have these batteries locking things in place, they cannot rise willy-nilly. They can only rise during a surge. And during a drain, they're supposed to fall. So right now, oh, they're flipping polarity. This is the weirdness of this circuit. It's the weirdest thing you ever did see. So let's see, we're draining. So that means we're still rising. See, because it crossed the midline and now it's rising. So we have to toggle back to get rid of that. Yeah, it's still rising. Okay. Just have to go through this a few times. See, now it's falling, but it's probably going to cross to the other side because it's really seeking the inverted polarity. What happens if I toggle this near the midline? Nothing yet. Usually this works. For some reason, it's not working yet. Maybe because I didn't let it surge enough. That was probably the problem. Because surge is the honesty of the system. Everything else is contrived at this point. So let's let it surge for a while, because that's probably what's needed that will help to balance out the system. So it won't behave anomalously. We want it to behave the way it was designed to behave. Alright, so we see the surge occurring as an AC condition shaped like Gabriel's trumpet. If you look up on Wikipedia, Gabriel's trumpet, it has to do with a very interesting mathematical anomaly. But that's the way I liken these surges, because it's, once this balances out, oh, see, that's it, it's not balanced. See, the voltage is balanced, but the amps are not. But as they grow, they will position themselves balanced along the midline. I think that was the problem. It was too imbalanced. So let's see how we're doing here. The amps are still rising. Okay, so it's still not balanced. Yeah. They still want to hug. This one wants to go below the line, and this one wants to go above the midline. And they haven't reached the target yet. My target is 10 milliamps, so. But it did quicken things by toggling back and forth. I think. I didn't have to wait as long. Yeah, right. I don't have to wait. Now, if you want to wait, that might be in your favor, you know. This is still not much time. But when you consider real time, you know, how easy would it have been for me to do this? I couldn't have. So actually it's best to just let it surge, you know, come away from drainage and let it surge until it reaches your target, and then it'll be balanced by that point. And you'll be able to respond, because if you read this text here, what I'm saying is there were no computers or motor controllers in Tesla's day, and so the operator was the controller, and so it's kind of ridiculous to think that we can't do this without being dependent on all of the artifices that we have come to become dependent on, you know, we take for granted. So there is no motor controller here required. And that's what I was shooting for, was a design that would take into consideration that you have to strip away all of the excess baggage that electric cars have in today's world and bring things back down to their simplest level to appreciate what Tesla was dealing with in his day and age. So now we have amperage still rising, which means it's still not balanced. It should be falling when we drain. That's the correct behavior. So I'm kind of happy with this. The only thing, wrong is this high level of capacitance, which will cause you to lose your voltage. On the one hand. Yet on the other hand, since the LMD modules can make whatever current you want, well, it's I don't know, in real life, because the simulator is running at such a slow speed, it's hard to know in advance what it would do over a long period of time. I have no way of knowing. Oh, now I'm up at 300 amps. Am I rising or falling? Looks like I'm going to be falling now. Yeah. That's what it looks like. No? Yeah, no, it's falling, it's dropping. That's right. So I've hit pay dirt. So now the amps are falling, and we have 300 volts locked in. And the amps, as you can see now, are falling. We're below 300 amps here. Then, oh well, not quite yet. That's on the leading edge. Yeah, the trailing edge is still showing the prior. This is a span of time. Oh, you see the little jump down there. So this is my latest attempt to create a simulation that's buildable, that's realistic, and that can point us in the direction of solving this mystery of Tesla's Pierce arrow demonstration. And the 12 radio tubes may have been a charade. He may never have used them. He may have simply had a very large capacitor inside that wooden box. Where he got it from, I don't know. Maybe somebody delivered it in the middle of the night. But in those days, components would have been larger than what they are today, in today's world. So, 2-foot long box and a foot square, basically a 2-foot rectangle, that would have been a very large capacitor, and something sufficient to hold enough volts to run the AC motor. Basically, that's all it was, and that's all he had to connect, because remember, it was 2 heavy cables. That means 2 connections. Now in this case it's in parallel, which means one cable would go how would that work? It would have to be a cable that loops, or 2 cables that loop. 2 heavy cables. 2 heavy cables doesn't say whether or not they were bent in the middle. Because if they were bent in the middle, then he could have just connected this at the tip of the U, and this end at the tip of the U of the other cable. And heavy cable makes sense if it was high voltage. They would have been high voltage cable. Anywho, I think that's all was inside that box, was a precharged capacitor storing the required voltage for that particular demonstration, that particular AC motor that was being used in that demonstration to push around a heavy car. 4,000 pounds is a lot of torque requirement. So probably 300 volts may not have been enough, I don't know. But for an AC motor, maybe not much more, maybe about that. Yeah, who's to know? Yeah, AC motors, they run a little higher in amps, actually. I think the Tesla motor is somewhere in the vicinity of 300 to 400 volts, but its amperage is 1.5 kiloamps. But here again, drainage is a DC modality, and you saw how things flip, so there has to be some switch to flip the polarity of the motor coils, because you wouldn't want it to go in the wrong direction. Now, the switch might be an automatic relay as part of the circuitry to sense the polarity and then make up the difference. Because every time you toggle from surge to drain, it looks like the polarity changes, or in a random fashion, something that's not predictable. So there has to be a sensing device to flip the polarity the correct way, so we don't get the AC motor to be draining, the universal motor to be draining in the wrong polarity. Now, it seems doubtful he was using a three-phase motor. If this circuit has any relevance, any accuracy to what he was dealing with, so it would have had to been a single-phase AC motor would come the closest to a universal motor, and he would have had to have had it designed to be a universal motor, which is not that hard in today's world. We take it for granted. In Tesla's day, it might have been a little extra requirement that maybe they weren't familiar with. I don't know how when universal motors were invented, so I'm not quite sure. Anywho, so our amps have gone down to 280 amps, and the voltage is still the same. So if we wanted to surge this, do we really want to? Yeah, I suppose so. Huh. 1 amp in surge mode? Wow. And it gives us 200 or 300 amps in drainage mode. 300 to 1, that's interesting. Well, anyway, so that's enough playing around with the circuit. So I hope you understand the principle involved of how to operate the thing. The principle of parametric oscillations is a whole nother deal, and it's so new for people that it's quite unfamiliar, and it's so tempting to try to analyze a parametric oscillator in terms of a driven oscillator, something that people formally trained are more familiar with, and they only think in that one modality. A tank circuit is a driven oscillator. A parametric oscillator is totally different, and fortunately I do not have formal training, so I'm very flexible. I can learn new concepts and not get hung up on any kind of formal programming that my brain may have been subjected to, which it has not been. So I catch on a little quicker than most people, but I have to fumble and stumble and try this and try that and follow my intuition, and but the simulation helps speed up my learning curve. It really does. It really helps. And I think it's just evoking memory, some kind of memory deep in my soul that it's evoking, or else I wouldn't have had so much success so quickly. But there's always some caveat that's a little bit unrealistic, and ideally this should be a very high farad, capacitance on this capacitor to keep the voltage steady eddy, so you don't lose your voltage over the course of your driving experience. But recharging the car at night now is simply a question of plugging in this capacitor into your house wiring when you go home at night into your garage to get the voltage that it requires. And how long does that take to charge a capacitor to sufficient voltage? It really doesn't take that long, because it doesn't hold much current value. Its actual storage is volts, which doesn't take any time at all to charge up a capacitor. It takes some time, but overnight would be easy. It would be done lickety-split. And the LMD modules, they surge so quickly that it doesn't take very long in real time to develop amperage to complement the voltage of this capacitor. So one component here delivers the voltage and everything else delivers the amperage. And the batteries have nothing to do with delivering amperage. They have to do with thwarting amperage, too much amperage from being delivered per unit time. That's the most difficult thing to regulate, is a surge, to prevent it from exploding in your face. The last thing you need are components blowing up in your face or blowing up underneath your car. It's the last thing you need. So it was pretty touchy for me to try to figure this one out. But you'll notice the coils are swapped polarity on the coils. That's to make sure that when they drain in the same direction. See? These pair go up, and these go down, and then these coils are going down as well. See? They match these. But of course, these would flip when the amperage flips. So there's nothing, standard or rock solid about this direction. I suppose we could put diodes, but see, an LMD module cannot be regulated by a diode. It has to be allowed to oscillate. But in drainage mode, we could have switched diodes into these. Well, actually, the direction right now is against the flow of this. That's interesting. It shows how little relevance the current of the battery has on this circuit, because this is going up, that means going to the right here, that means going against the diode here, which of course is not going to happen. So it shows that the LMD module is pretty much controlling its flippability of amperage, direction of flow of amperage. So in drainage mode, maybe we'd want to force it and put a diode in there, and then take the diode out when we go into surge mode. But the simulator, this simulator is very limited on what it can do. It can't do a complicated circuitry, especially one that's performing over unity, parametric, escalation. So I have to limit myself in terms of complexity, or else I get convergence error messages. So there's still room for improvement on this circuit to make it more conducive. Maybe diode is the way to go. Maybe a relay that flips polarity of the wiring of the coils, the motor coils, is the way to go, including this capacitor, to maintain the same sine value of current at all times. Whatever works, whatever's the simplest that works, manageable, cost effective, all those things. I think that's everything I wanted to say. Okay. Happy simulating. Here it is. Find the off switch.